Let's take a look at section 6.6, which is rational exponents. So this is a new section that you want to pay careful attention to. However, the good news is if you have a strong understanding of exponent rules, rational exponents shouldn't be too tricky. So what is a rational exponent? A rational exponent is simply a exponent that's a ratio. AKA a fraction. Now, two really important things, okay, is that all exponent rules apply. So the product rule, when we are multiplying, we'll add the exponents. When we're dividing, we'll subtract the exponents, so forth. And the other thing is, never want rational exponents in a denominator. Okay, so those are two important things to remember about rational exponents. All right, now the other big important thing for today's lesson is converting between rational exponents to radical exponents. So if I have some rational exponent that is m over n, I can rewrite that instead of with exponents, but as a radical. So the denominator becomes the root and the numerator becomes the power. So let's do one example before you try some on your own. If I simply had x to the 2/3, this would be equal to, the denominator is 3, so my root is 3, my base is x, and the power is what the numerator was, which was squared. Okay, so this conversion is going to be very helpful to help simplify. Okay, so these two are the biggies to know. Rational exponents are just exponents that are fractions. All exponent rules apply, and you never want a rational exponent in the denominator. And the other big one is our conversion between rational exponents and radicals. So let's start with that conversion. First example, say write with the radicals and simplify if possible. So we're going to go with the fact that my denominator is 3, means I'm going to have a cube root. Now notice that negative is not being applied to the power. It's on the outside. So I'm going to keep the negative on the outside. And then I have 64 to the first power on the inside. Now you don't need the 1. But again, denominator is the root, numerator is the power. And because that negative is not in parentheses, the negative stays outside. Now I simplify. I have the negative out front, and the cube root of 64 is 4. So you may not have known by looking at number 1, like, oh, what's 64 to the 1/3 power? But what that really means is just what's the cube root of 64. Okay, let's look at number 2. Number 2 says 81 to the negative 1/4. So be careful here. If I have 81 to the negative 1/4, I have to first apply my exponent rules. We never want negative exponents. So this will be 1 over 81 to the 1/4. Now that we have a positive exponent, we can actually simplify this. So we're going to change this to radical form. So this will be the 4th root of 81. And now I ask myself, is 81 a perfect 4th power here? And yes, the 4th root of 81 is 3. So this is simply 1/3. No rationalizing involved. Okay? We're going to do number 3, and then I'll have you try number 4. So for number 3, we are multiplying. Now we're just going to use exponent rules. So we don't necessarily need to convert to radicals right now. This is saying multiply with the same bases. So when I multiply, I add the exponents. So this will be keep the base of 27 and add the exponents. The good news here is that those exponents have the same denominator, so adding them is pretty straightforward. This gives me 27 to the 5/3. Now let's convert to radical form. Root is the denominator, so cube root of 27 to the 5th. Okay, So if I simplify that, right, we have that the cube root of 27 to the 5th would be, if I take that out, that gives me 27 on the outside. And then we have the cube root of 27 squared. Is there anything else I can do to simplify that? I'm going to give you a hint. Yes, there is. See if you can break that up even more and try to find the answer. After you do that, try number 4. So remember here, because it might be a little blurry looking, this is really saying 12 to the negative 1/2. All right, now let's go in reverse. So now we have a radical, and we want to write this with rational exponents. So my base is n, the root is 3, so that's my denominator, and the power is 2, that's my numerator. So this is simply just n to the 2/3. Okay, for number 6, there's 2 different things we can do here. The first is to simply just convert to those rational exponents. Remember that there's really a 1 on the 16, so I'll have 16 to the 1/3, a to the 5/3, and b to the 7/3. If you can reduce any fractions, do so, but I can't. The more broken down version, which is better for us to do, is to recognize that this 16 can really be 8 times 2 times a to the 5th times b to the 7th. And I see that because I can simplify. So the cube root of 8 is a 2. So that guy doesn't need any rational exponents. Now what's left over, so we took care of that. Now what's left over is the 2, a to the 5th, b to the 7th. So now I have a 2 to the 1/3, an a to the 5/3, and a b to the 7/3. So you may see either option, okay? This one where we simplify first, or where we just write everything with those rational exponents, including the 16. All right, you try number 7. Write that with rational exponents. If you can simplify, simplify. All right, now we have a bunch of simplifying problems. When we're simplifying, we need to remember no negative exponents. We need to remember that there can't be any rational exponents in a denominator. And the reason for that is we just saw that rational exponents can convert to radicals, and we never want radicals in the denominator. So therefore, no rational exponents. We can't have a complex fraction, so no fractions within fractions. Exponents can be fractions, of course, though. And then the index of any remaining radical is the least number as possible. So can you break it down any further? So let's take a look at some of these, and then I'll have you try some of them as well. So for 8, this is pretty straightforward. The bases are the same, and we're multiplying, so we just add our exponents. A to the 2/7 plus 4/7. Power roots are the denominators are the same, so we simply just add, and that gives me a to the 6/7. No negative exponents, no improper fractions. We're good to go. Number 9, we are multiplying. Now notice, usually when I multiply radicals, inside with inside, outside with outside. But these are different roots. So the first thing we're going to do with these is, before we would say, oh, we can't do it. Now we can. We're going to convert this to rational exponents. So this is 2 to the 5/3 times 2 to the 1/4, right? Our power is our numerator, root is our denominator. Now, what I'm going to do, those bases are the same, so I'm going to add those exponents. So this is 2 to the 5/3 plus 1/4. Little extra work here because we need a common denominator. So I'm going to make that denominator become 12. So we have 2 to the 20th 12ths plus 3/12. When I put those together, we get 2 to the 23rd 12ths. Now, because this was radical to begin with, we need to go back to convert that to a radical. So that is the 12th root of 2 to the 23rd. Well, can I simplify that? Yes, 12 goes into 23 once. So a 2 will come out, and I'm left with 2 to the 11th inside. And there's my answer. Okay, you try number 10. Pretty similar, not as high of numbers though. Okay, let's look at 11. So 11 here says 1 over 5 to the 1/2. The problem with this one is that we have a rational exponent in the denominator. I don't want rational exponents. So what can I do here to make this a whole number as an exponent? I want this 1/2 to become a 1. Well, remember, when we multiply, we add the exponent. So what I'm going to do is I'm going to multiply by 5 to the 1/2 because 1/2 plus 1/2 makes a whole. So if I do that to the bottom, I must do it to the top. And the reason I'm using the 5 is because when we multiply, the bases must be the same. So now in my numerator, I have 5 to the 1/2. And in my denominator, I have 5 to the first power, or simply just 5. If I look at this answer, there's no rational exponents in my denominator. There's nothing else I can simplify. Please understand we cannot cancel out the 5s. Okay, they have different powers, so we're not going to actually combine them. So this is all my answer is. You try 12 and 13 using that same process. We don't want 7 to the 2/3. We want that to become 7 to the 1st. So what would I multiply by? And we don't want 2 to the 3/2. We want that to become a whole number down there for an exponent. So try those two problems. Okay, now we have 14. 14 is different because there are two terms. So if it was just x to the 1/2, I'd multiply by x to the 1/2. But because there's two terms, we're going to use the conjugate, just like we used a conjugate before. So the conjugate of x to the 1/2 plus y to the 1/2 is x to the 1/2 minus y to the 1/2. And we'll do that up above as well. So now I FOIL. X to the 1/2 times x to the 1/2, we keep our bases, we add our exponents. 1/2 plus 1/2 makes a whole. Now we multiply x to the 1/2 times negative y to the 1/2. Those we can't actually put together, so it's simply as is. Now the inside, negative 1/2 y to the 1/2 times x to the 1/2 is another negative, and I'm going to put the x term first. And then lastly, negative y to the 1/2 times negative y to the 1/2 becomes positive y to the 1st. Those are the same bases, so I add those exponents. All over, now we FOIL that denominator. Those middle two terms should cancel. So x to the 1/2 times x to the 1/2 becomes x to the whole. We have a negative, and then we have a positive, so those middle terms cancel. And lastly, minus y to the 1st because we add the exponents. Now I will clean up my numerator. We can put the two middle terms together. So I have x minus 2x to the 1/2, y to the 1/2, plus y, all over x minus y. And again, there's no canceling I'm going to do here. Even though there's x up top and x on the bottom, they're connected with those subtraction signs. All right, I want you to try 15. This is just exponent rules. So use your exponent rules, power to a power, we multiply, and then try to do any rationalizing that you may need to use. All right, and the last one we'll do together, and that's number 16. So number 16 says the 6th root of 27. Well, is 27 like a perfect 6th power? Is there something times something times something times something times something times something that gives me 27? No, there's not. So for this problem, I do see that 27 is a perfect cube. So if I recall, 27, the 6th root of 27 is really the same thing as 27 to the 1/6. Well, 27 to the 1/6 is also the same thing as 27 to the 1/3 to the 1/2. Because power to a power, we multiply. 1 times 1 is 1, and 3 times 2 is 6. If I convert that to radicals, 27 to the 1/3 is the cube root of 27. And now that will be to the 1/2. Well, the cube root of 27 is 3. So that's saying 3 to the 1/2. Now, last but not least, 3 to the 1/2 means to take the square root of 3. Can we do that? Nope. So we leave it as is. So when you see some numbers like this, if the number inside is a perfect square, a perfect cube, a perfect fourth power, then as long as it can, if it's a perfect square, it could go into your root, or a perfect cube, it can go into your root, you always have more simplifying that you can do. All right, try those other problems, and then we'll do lots more practice tomorrow.